Hello everybody, welcome back. So this video is a continuation of the previous video on conditional probability. Just to recap, in the previous video we looked at two examples. So one example of throwing a fair die, six-faced die, and I asked you what's the probability of getting a 4? That probability is 1/6 because there are 6 possible outcomes and 4 is one of them. So we're assuming that each outcome is equally probable, and therefore the probability of getting a 4 is 1/6. The other example, and that was an example of a conditional probability, was the probability of getting a 4 assuming that you got an even number. Since there are a total of 3 even numbers that you could get when you throw a fair die, namely you could get a 2, you could get a 4, you could get a 6, then the probability of getting a 4, assuming that you got an even number, is 1 divided by 3. And so that's an example of a conditional probability. So what we're going to do in this video is to talk about all this a little bit more generally. And so this means a little bit more mathematically. So let's start with a probability of a generic event A. And remember that we are thinking of events here in terms of sets. So sets are a collection of objects of whatever kind. And so we write the probability of A as PR and between parentheses A. And so what is the probability of A? What is one way to think about the probability of A? And in terms of sets, one way to think of the probability of A is as a ratio between the number of elements in A divided by the number of elements in omega. And omega, so that the big O, the Greek letter omega, that represents your sample space. So that is the set that contains all the possible outcomes. And pictorially, this is represented as a rectangular, a big rectangular, omega. And then your set A, which represents the event of interest, is drawn as a circle. Okay, so nothing new from here. So far we have the probability of a generic event A given to us as the ratio between the number of elements of A divided by the number of elements in your sample space, omega. Now, on to conditional probability. So what is the probability of an event A, a generic event A, conditional on some other event B? And again, A and B here should be thought in terms of sets, because events, we're thinking of events in terms of sets. And as a definition, we can think of this conditional probability as, again, as a ratio between the number of elements in A intersection B. So remember that symbol, that upside down U, is the intersection. So it represents the intersection between two sets. So the intersection picks out the elements that are common to both sets, if you remember. And then we divide that by the number of elements of B. And we can represent this pictorially, if you want, using this big circle. So the red circle is for the set A, and the blue circle is for the set B, and then there is the sample set omega in the background. So now what we're interested here in is the probability of A, so the probability that something, let's say, falls within the red set A, conditional on B. So our focus is going to be on B, no longer the set omega, the big set omega, but the set B. And so I draw a little thick black line around the set B, because that's the condition we're interested in. So just to recapitulate, I want you to see the difference between these two different probability statements. So the probability of A is the ratio between the number of elements in A divided by the number of elements in omega. So our focus here is the entire set omega, and we are wondering how much of omega is covered by A, or how many elements that belong to omega belong to A. So that's the way we should think about the probability of A. Whereas when we think of the conditional probability, so the probability of A conditional on B, our focus is no longer omega but just B. And so you see that in the denominator, omega becomes B. We don't need to count the number of elements in omega, but we need to count the number of elements in B. And so our B becomes the omega when we talk about conditional probability. And then the numerator, well, the numerator, we need to consider the elements that are both in A and in B. And that is why we have the intersection. And then we take the division, so we divide the number of elements in A intersection B divided by the number of elements in B, not in omega, and this gives us the conditional probability of A conditional on B.